Good morning. This presentation summarizes the Boston University effort that we have undertaken in the phase 1 of the DARPA SyNAPSE project. In the project, we were asked to focus on three main goals. The first pertains architecture, and the goal here is to develop a whole brain system circuit that defines the function and connectivity of constituent neural models. The respective deliverables of the Boston University team is MONETA, which stands for Modular Neural Exploring Traveling Agent, and in particular its whole brain system diagram. The second goal pertains simulations and is to demonstrate dynamic neural activity, network stability, synaptic plasticity, and self-organization in response to sensory stimulation and system-level modulation reinforcement in a system of roughly 10 to the 6 neurons. We have two deliverables that match these goals. The first one is the so-called neural soup, which we have presented already in August 2010. Which has 10 to the 6 neurons, and the second one is MONETA, which is our animat implemented in both virtual environment and robotic platform. The third goal pertains environment, and in particular to demonstrate virtual visual perception, decision and planning, and navigation environments with a selectable range of complexity corresponding roughly to the capabilities across 10 to the 4th range in brain size in small to medium mammalian species. And the deliverable in this case is MONETA, implemented in the virtual environment. So in terms of architecture, MONETA again is our deliverable, and it's our whole brain system that consists of mainly three macro circuits: a sensory microcircuit, a motivation, and a navigation one. The task that we've been testing MONETA with is the so-called Morris water maze. It's a classic rat experiment where the basic paradigm is as follows. The experimenter places a rat in a water tank. Rats don't like to stay wet, and they are trying to escape they're trying to escape the maze, and the only way out of the water is through a submerged platform, which is of course invisible to the rat, but it can be located with training thanks to a few landmarks which are placed at the border of the pool. Down here you can see a typical run of the rat. In the first trial, the rat of course doesn't know where the platform is, or doesn't even know that the platform exists, so it runs around the water tank trying to find an escape. But as trials go ahead, the rat learns the location of the platform, and for being located in any place in the platform, it can self-localize itself pretty quickly and then swim to safety. This is the macro circuit again, a little bit more detail. Each box represents, whenever possible, represents a particular brain area or a set of brain area that implement a particular brain function. MONETA has in total 32 million neurons and 13 billion synapses, and we have to keep in mind that the mapping is done keeping into account the population coding of our system. So each cog element corresponds to 100 neurons, and each cog weight or projection correspond to 100 biological synapses. The second goal was simulations, and the goal here was again to demonstrate dynamic neural activity, network stability, synaptic plasticity, and self-organization in response to sensory stimulation and modulation reinforcement in a system of 10 to the 6 neurons. The deliverables that we have performed for this particular task goes under the name of Neural Soup, and is basically a simulation where we are trying to combine two different aspects of neuronal self-organization. The first one is the ability of a network to learn some representative information, for instance, receptive field through exposure to natural images, and the second is the ability to create an homeostatic environment for itself, so the ability of the network to self-regulate its overall level of activity by not allowing the network to either the activity of the network to either go to zero or saturate to infinity. This is the network, which already I have described in detail in August, but just to refresh the memory, we have a set of natural images which is fed to a receptor. The receptor layer feeds to a cortical layer, if you will, which is organized in terms of a non-center off-surround organization, and learn basically a receptive field directly from the receptor layer through a modified instar learning law. The novel part of the network is represented by two multiplicative scaling component, one excitatory and one inhibitory, and these are in turn regulated by dynamic equations, which in turn have the property of stabilizing the activity of the network by decreasing or increasing the amount of excitation and inhibition, therefore maintaining an homeostatic level of activity. These are typical results of a single run. On top we have a snapshot of the inputs across around 50,000 presentation of snapshot of natural images. Down here we have learned receptive fields, and you can see that the receptive field starts to shape at the beginning, but it remains fairly stable throughout the duration of the simulation. And this is very important if you consider what we're doing with this input. So we are basically blasting the network with ramping up with a ramp of activity. You can see it here in the input trace. We are ramping up the activity, ramping it down, and then blasting the activity with a high frequency input. And you can see in the time average activity below how the networks basically after a few transient due to the fast increase in the simulation, it basically is trying to maintain an overall level of activity which is fairly constant. So this is an example of how we can combine homeostasis, or the ability to maintain a constant level of activity in the network, while at the same time implementing some sort of interesting plasticity. In terms of the environment, the goal here was to demonstrate virtual visual perception, decision, and planning and navigation in small to medium mammalian species. Again, the experimental protocol we have replicated is the Morris water maze, and you can see down here the typical COG simulation environment that a Moneta experimenter deal with on a daily basis. On top, we can see the Morris water maze and the rat running around in the virtual environment. Right underneath, you can see what the animate visual system actually sees. In the middle, we have the COG block diagram, and on the right, we have a few of the populations. In particular, this population pertain the navigation system, which are exploded, and the user can basically monitor them. We have the goal selection map, the familiarity map, which is a new component in Moneta and in general in the modeling literature, which I will explain a bit later. Basically, it's a map that maintains a location of the region visited by the animate to bias the exploration of novel environments. The obstacle map, which is basically a map of the learned obstacles in the environment. The Morris water maze, of course, doesn't have any other obstacle other than the border of the pool, and this particular run shows an animate which has already learned the task, so you can see that it has a very clear representation of what the obstacles are. And you also have the reverse spread, which is one of the mechanisms used by Moneta to basically generate a trajectory in the environment. On the left here, you can see a typical run of Moneta. You can see on the first try you have a fairly erratic behavior of the animate as it explore the environment and doesn't know about the platform. On the fourth run here, you can see that the animate is placed in the environment and then it shoots through the water tank to find the platform pretty quickly. I will give you a little bit more detail about a few of the modules developed by our team in Moneta, starting with the motivation and navigation system. The first novel part of the model is called the Curiosity Drive. The goal of this module is to promote the exploratory behavior to sample new spatial location. The Curiosity map is basically a neural map that is created in conjunction with its nemesis, which is the familiarity map. The familiarity map basically maintains a neural trace of the places that the animate is visited as it explores the environment. And the familiarity map basically excite with the off-center on-surround the curiosity map in order to generate activation in cells which are just around the area which have been explored, but they are not, but they have not been explored in the past. Therefore, this map basically guarantees that in the next iteration, the curiosity map will have activation around the areas of unexplored environment. Another interesting aspect of Moneta is the development of allocentric map, and the goal of these modules is to remember rewarded location in the environment, and at the same time forget location in the environment that have been rewarded in the past, but they are not rewarded anymore. For instance, in the Morris Water Maze, the experiment might shift the platform, the underwater platform. Therefore, the rat should forget or should discard where the platform was located in the previous trials. The learning law that we have used has two components, one that increase and one that decrease the synaptic weights. In particular, the weight between an active drive, in particular the drive here is the drive for the discomfort drive, and the goal location map. The connection between these two is increased whenever a drive is active, so there is discomfort. The rat is in a given location and the location is rewarded, so it has found the platform. At the same time, the map is decreased when an animate is in a given location, a drive is active, and the reward is not found. So this learning law is kind of different from many of the learning laws that we've been thinking that we were going to use, and it's actually a non-Hebbian learning law. You don't actually need the postsynaptic cell activity in order to learn, and that's an important aspect, in the sense that if we wouldn't have had COG, and if we would have had a different learning environment, then a different programming environment, or a more rigid hardware implementation, then we would have been stuck. Since this law, if it wasn't contemplated at the beginning, we were going to be in big trouble. Another interesting map formation in Moneta is the selection of the goal location. So this is a case in which you are basically combining different maps, in particular a learn map of the goal location where the platform is, and a curiosity map. And both of these maps are trying to drive the animate towards a given location. And this is a typical example of how when you have a large brain system and so few degrees of motor control that the brain can actually take control of, then you have to resolve ambiguities and conflicts between different brain areas that want to drive the animate in different places. And this is a typical task that has been proposed to be solved by circuitry located in the basal ganglia, and we've been trying basically to simulate some initial aspect of this circuitry in Moneta. In particular, the goal selection map receives input from both the curiosity map and the goal and the goal map in a non-center of surround neural map. In this map, also the obstacle map provides inhibitory input, and a winner-take-all mechanism basically selects the next available point. So this map is dynamic, in the sense that at the beginning the curiosity drive is fairly strong. It tends to bias the activation of this map, but as the goal location map becomes stronger thanks to reward, then the goal location map tends to win the competition and drive the animate. Also, another mechanism that we have implemented is a neurotransmitter habituation, and that basically allows a given winning point in this map not to win all the time through slow dishabituation or slow habituation of its neurotransmitter, and that basically allows the same location not to win the competition all the time. Another interesting aspect of the newly developed Moneta is its apparently random or erratic behavior. If you observe the Moneta animate as it runs around, it performs a series of apparently erratic movements, but it's interesting to note that this is nothing really erratic in this particular behavior. If we start from the same initial condition, this erratic trajectory is reproduced with 100% fidelity. And to the best of our knowledge, this kind of behavior is actually new and never been described neural modeling. And as I was saying, in order to perform the goal selection, we had to implement some sort of circuitry, which we believe, and there are strong reasons to support this claim that this competition is actually implemented in the subcortical circuit known as the basal ganglia, which receive a lot of convergent excitation from a number of cortices, starting from sensory, associative, and motor, and through a reduction of dimensionality and funneling and combination with external rewards, basically gates which particular representation in terms of motor command or sensory representation actually survives the particular competition. The goal-directed navigation, basically the goal-directed navigation describes a module which was already introduced in August, and that's basically the module that use the spread of activation between a given goal location and the goal and the current position of the animate in order to determine the next step. The collision of neural waves generated in the hippocampus between the current location and the goal location determines the next step that the animal should follow in order to achieve the goal. This model has been based on the thesis of one of us, Anatoly, who basically described this behavior already in previous experimental results, in particular in a T-maze. This has been combined with the novel idea of using the animate itself to learn the obstacles, and the obstacle basically are represented as inhibitory components of this map, and the neural wave then goes around the obstacles and determines the shortest path between goal and present location, even in the presence of obstacles. Another interesting problem that Monet has solved is the mapping between different coordinate systems. So whenever we have a large-scale whole brain system has different coordinate systems, sensory, motor, and allocentric, and a big problem in designing these modules is how do you map between them. So this is an example in which we need to map from allocentric or word-centered coordinate system to the motor coordinate system. So how do we go, for instance, from a condition in which we have a representation in word coordinate of where we are and when we want to go, to a situation in which we translate this information into the appropriate set of motor command to take us from here to there. And the idea here is to basically implement a neural-based strategy, which is basically a shifted connectivity map which has been again introduced in this modeling effort, that basically allows to map a particular shift between the current location and the desired location in one of these maps. When the shift is with the appropriate shift between the current location and the next location is achieved in a particular map. This map, for instance, in this case the southwest map, will translate into the appropriate movement that will take the animate in the southwest direction, that will bridge the gap between the current location and the desired location. Of course, we have also the different, the specular problem, which is to map between egocentric coordinates and allocentric coordinates. So, in this case, for instance, we have the inverse problem, which is, well, given a certain motor commands which I am executing, what are the allocentric coordinates where these particular motor commands map into the word coordinates? A typical example is the ability to map an obstacles. If I close my eyes and I start going around with my motor system, I can easily map the obstacle which I'm encountering by basically mapping the geometry of my motor commands into my allocentric representation. Without going into much details here, we basically use the inverse mechanism, which is use this shifted map of connectivity in order to map from the motor coordinates to the word coordinates. And this is a typical run of the animate, as it uses this mechanism in order to map the contour or the borders of the pool, as it basically the animate touches or hits the wall. A bit more detail about the sensory system of Moneta. Moneta visual system, it consists of two pathways, kind of mirroring what the primate visual system mirroring the organization of the primate visual system. We start from a visual input, which is filtered through a number of filter banks in the early visual areas, and these are then combined in a so-called saliency map, which is proposed to be implemented in a posterior parietal cortex, which generates an attentional focus, which in turn bias the what pathway. So there is a feedback between the what pathway and the where pathway, and that's also a novel component of the model. And the idea here is that whenever there is an active coding representation in the what system, so for instance, whenever the what system starts to recognize a particular feature which is recognized in the past, sorry, a particular object, then it biases the where system to basically keep scrutinizing the particular spatial location around the one where the object has been recognized. So by doing so, the system basically implements a sort of a scrutinizing behavior, which basically allows the what system to gather more evidence as time goes on. The what system, we have developed two versions. The first version was put in place, in order to quickly prototype Moneta, and there was basically a color-based what system, which uses basically colors in order to perform classification. We have also developed, and we are in the process of porting to Moneta an edge-based visual system. So the the what system starts again with attentional focus. It has a set of color tune cells and spatial invariant color tune cells implemented in our V1 and IT. And this information is then fed to our prefrontal cortex when we have an object category classifier. This is a typical confusion matrix of one of the run of the models. In a confusion matrix, you want to, of course, have strong diagonals, which means that you're correctly classifying information. If you have misses, then you want them to be near misses or misclassification around the boundaries, around the diagonal, and that's exactly what we get. Again, we are implementing a system that goes beyond color and also implements edge-based features. And the way we are designing this is through self-organization. So this is a typical run of the model as it runs around again the Morris water maze. We have a visual input, and we have a set of simple and complex cells mirroring the V1 equivalent, and this information is then fed to V2, and these are higher order representation. You can see how this V2 representation starts to be expressed in V2 as learning goes on. So we plan to include this more refined system in the next couple of months. Finally, we have done some implementation of Moneta in robots. In particular, Moneta has implemented two of the three navigation strategies. The first one is the one we have already seen, topological navigation, which is movement along known path, which uses the hippocampus. Another one is a basal ganglia related strategy, which is basically to use memory of motor commands in order to reach a particular goal, which is, for instance, take a right, and a left. A third strategy is a visually based navigation strategy, which is I see where I want to go, let me go straight to it. And in order to do that, we've kind of inverted our modeling philosophy, which is to go from the robot back to Moneta in the virtual environment. The robotic platform we have developed is called VGuar, which stands for Visually Guided Adaptive Robot, and is implemented in our usual cheap, cost-effective platform, which consists of a Roomba with a netbook on top, which communicates to a server, which in turn communicates to the cog-based brain. This is a typical example of Viguar, whose behavior is basically to get interested in a particular object, choose an object, reach it, and learn its reward value. So in this particular case, we have attached rewards to a positive reward to a green object and a negative reward to a red object, with then the consequence that, you know, after a few encounters, the robot basically decides that it wants to avoid red things and tries to reach green things. So of course this is a proof of concept of behavior which are way more complex, which is the ability, for instance, to learn initial association with a particular sensory stimulation and generalize these through, for instance, secondary conditioning. An idea that we are implementing in these days is to basically use optic flow in order to and reinforcement learning in order to teach a land robot and a UAV to basically avoid a collision with walls. Finally, we are starting to use Item for our modeling effort. Item again is the iterative evolution of modern platform, which will basically transition us, which will basically transition us in the next, which has started already actually to transition us from our primitive phase, in which we have one model, one modeler for each model, to a phase in which we have one model and one model and several models, and we have been using this particular framework in order to develop the components of the new path integration systems in the navigation system, with considerable savings in modeling time. Finally, it has been a very productive year, and we thank DARPA for making this happen. In the past 12 months, we have had two cover page articles published, one on the IEEE spectrum done by Ben and myself, and the other one in collaboration, of course, and led by Greg and their colleagues at Hewlett Packard. Both of them made it to the cover page of two prestigious magazines. We also have published 4 conference papers, and in total, you know, between the 6 publications, 3 of them were co-authored with Hewlett Packard. We have published an online article on the neuromorphic engineer, 5 abstracts, 4 conference presentations, and 14 non-conference presentations. We also have had quite a bit of media coverage. This is just a small sample of the coverage that we had in the past, I would say, 3 to 4 months. It goes from the IEEE Spectrum to a few editions of Popular Science, MSNBC, Slashdot, and an upcoming New Scientist article. This is, of course, being rewarding from the psychological point of view, but that was not the goal. The goal was to become visible, and that has been a success. We've been contacted by a large number of companies, and small to medium to large sized, operating in different fields, by governmental agencies and university nationwide and international. So we are very pleased with the work, and we thank again DARPA for making this happen. Thank you.